Hello and welcome to this walking talking mock looking at question 2 of the high demand electric circuits questions. The diagram shows a temperature sensing circuit used to control a heating system in a house. Okay, so we've got a circuit here, we've got a fixed resistor, I've got a thermistor here. That hockey stick tells me it's a thermistor, which you might recognise from when you do heating curves, if you remember. So time along there. Heating curves do this amazing thing where they do this, and they flat line plateaus, where this is the boiling point, this is melting point, and then boiling point, and that hockey stick pattern has been taken from that to indicate temperature. We've got a voltmeter and we've got an ammeter. So let's have a go through the answers. What quantity does the ammeter measure? Well, the ammeter measures current. Okay, amp meter or ammeter. The current in the circuit is 3.5 milliamps. When the potential difference across the thermistor is 4.2 volts. Calculate the resistance of the thermistor. Okay, so it's a calculate question. I'm looking for resistance. I've got current, 3.5 milliamps. And I've got potential difference across the thermistor of 4.2 volts. It's worth 3 marks. So this looks really simple. I'm just going to put a line down the side here, so I can I've starred the values I need. I've starred the value I'm finding. I've underlined the key information. I'm going to rewrite the values. So the current in the circuit is I. It's a series circuit, so the current is the same all the way around. I, remember, means intensity of current, intensity to current. Now I is 3.5 milliamps. I'm just going to rewrite that straight away in amps. I'm going to convert, even if I don't need to later. I'm going to do it now because I will get credit for it. So 3.5, and whenever I see milli, I just replace milli with divide by 1,000 amps. I'm going to leave it like that. And then V, potential difference is 4.2 volts. I've got to calculate the resistance, so I can remember that the formula I'm going to have to use is V equals IR. I'm going to substitute the values in before I rearrange. So 4.2, I'm always going to make sure as well, only have a 1 equal sign per line. 4.2 equals I, which is 3.5 divided by 1,000 R, and I should really calculate that just to make sure. So I'm going to do it on my calculator, even though I'm quite happy 3.5 divided by 1,000. I just want to make absolutely sure. So R is equal to 4.2 divided by 0.0035. So 4.2 divided by 0.0035. Just check on my calculator before I press equals. Equals is equal to 1,200. Okay, so 1,200 ohms. Most common mistake here is people will forget to convert milliamps to amps. Calculate the charge that flows through the thermistor in 5 minutes when the current is 3.5 milliamps. So it's another calculate. I've got to find the charge. I've got time is 5 minutes. Current is 3.5 milliamps. Okay, this question is loving the conversions. It's worth 3 marks again. So I know that Q equals IT. Charge is current times time, because current is the amount of charge in 1 second. So if we times that by time, we get the total amount of charge. So current times time is the total amount of charge. I've got I, which is equal to 3.5 milliamps, which is equal to 0.0035 amps. I've got T, which is equal to 5 minutes. So T is equal to 5 times 60, which is going to be 300 seconds. Time needs to be in seconds here. So the current is 0.035 times 300 gives a total of 0.35 times 300 equals 1.05, and they've given me a unit already over there, coulombs. So 1.05 coulombs. Explain why the potential difference, it's V, across the thermistor changes as the temperature in the house decreases. Okay, so I'm looking at temperature. It's worth 2 marks. It's 2 marks, so 1, 2, after 2 different points. Well, this is a thermistor, isn't it? So why does potential difference across the thermistor change? Well, as temperature decreases, as temperature decreases, so normally as temperature decreases, resistance decreases as well for most devices, except the only time that's not true is for a thermistor. So thermistors and LDRs are the only devices we need to know about that when they absorb energy, their resistance decreases. So when they lose energy, when their temperature increases. So as temperature decreases, resistance of thermistor, temperature decreases, so the resistance of thermistor increases. As resistance increases, potential difference, PD, which is fine for potential difference, it gets more difficult for each coulomb of charge, for each gang of electrons to get through. So because it's more difficult to get through, they transfer more energy each. Yeah, it's like trying to squeeze through a gap. The smaller the gap you're trying to squeeze through, the more energy you're going to expend doing it. Okay, so as resistance increases, PD also increases. The circuit shown in the diagram can be modified to turn lights on and off by replacing the thermistor with a light-dependent resistor, an LDR. Draw the circuit symbol for an LDR in the space below. Okay, so let's imagine I have no idea how to do this. I'm going to break it down. I'm going to say, right, I've got a resistor first of all. It's a type of resistor. Because it's a type of resistor, I know it's got to have that rectangular box. Okay, I know that. And it'll have a wire coming in like that. The wire, there isn't a wire inside it. The rectangular, white rectangular box means resistor. A fuse is a special type of resistor that has a thin wire running through it, which is why we draw the thin wire. It has light, and the light in this case is incoming. It doesn't give off light. So because it has light incoming, I know I need 2 little arrows. They indicate light. So light dependent resistor. And the last thing it's got is a window. So a circle just means a window. Okay, so that's my light dependent resistor right there. Okay, hope that's useful. I'll see you soon.